Hello everyone, myself Chandan, working as a guest lecturer in University College of Science, Tumkur University. In this video, I have explained the rank-nullity theorem in vector spaces. Of course, before start of this theorem, we have to thorough with some results as well as some definitions regarding these vector spaces. So I have just explained those definitions as well as some theorems. Just explain a statement of some theorems. So firstly, what do you mean by basis of any vector space? Suppose a set, suppose V is a vector space, and suppose S is a subset of V. Then this set, suppose this set is a basis of V, then it must spans a vector space. It must generates a vector space as well as that set is linearly independent. And in fact, suppose a set is linearly independent. If you check for linearly independent, first we have to consider the linear combination of those elements in that set. Suppose this is equal to some a1, a2, so on up to an. If you check for linearly independent, first we have to check the linear combination. We have to consider the linear combination of these vectors. That is some alpha 1 into a1, alpha 2 into it, sorry, plus alpha 2 into a2 plus 1 plus alpha n into an is equal to 0. And suppose this every elements in the field, these alpha 1, alpha 2, so on up to alpha n are the elements in the field. Suppose every element, this alpha 1, alpha 2, so on up to alpha n becomes 0, then this set S is linearly independent. So suppose any subset of a vector space must be a basis, it must spans a vector space as well as that set is linearly independent. Suppose if that set is linearly dependent, then it's not a basis. And secondly, suppose T from V to W be a linear transformation, be any linear transformation, and V as a basis, then this basis elements of V always spans a range space of T, but it need not be linearly independent. Firstly, I just explain what we mean by range space R of T. Okay, this is N of T, null space of T. This is null space of T. Null space of T is nothing but set of all elements in a domain space such that elements map to zero elements. That element must be mapped to zero elements in a this is codomain range. This is codomain. Null space of T is nothing but set of all elements in a domain space such that is mapped to zero. That is meaning is that images must be zero. This is nothing but null space of T. Then what do I mean by range space of T? Range space of T is nothing but it is, and in fact this null space of T is a subspace of domain space. Null space of T is a subspace of domain space. Remember this one. N of T, this is just a null space. Null space itself forms a vector space. Null space itself spans a vector space. Vector space, which is nothing but null space, is always a subspace. N of T is always a subspace of domain space. Subspace of domain space. There R of T. R of T is nothing but range space of T. Range space is always a subspace of codomain space. Range space is nothing but set of all elements T of V, where V is a element in domain. So R of T always spans a subspace of codomain space. N of T always spans subspace of domain. R of T always spans subspace of codomain space. Okay. Let T from V to W be a linear transformation and V as a basis. T from V to W be a linear transformation and V as a basis. then this basis elements of domain space always spans range space of T, but this set need not be linearly independent. This set need not be linearly independent in R of V. Suppose V is a domain space. V is a domain space and it has a basis. And it has a basis. Call this S is equal to A1, A2, so on up to AN is a N are the basis elements of this vector space. Then these basis elements always spans range space of T, that is their images of basis elements. Then images of basis elements of the images of then is a basis then images of basis elements of V always spans range space of T, but it need not be okay. Suppose this S is a basis elements of domain space, then their images are T of A1, T of A2, so on up to T of AN. These elements always spans the range space of T. But these elements need not be linearly independent. In R of T. Everyone as a simple proof, but I just now I just explaining the some results, that's all. If you want a proof, you can check in any books. Just you can prove simply that the null space is a subspace of, we just consider two elements, and for a subspace we have some condition. If you substitute in that, we will easily arriving at the results of null space is always a subspace of vector space. So basis mean a set is that set is linearly independent as well as spans a vector space, and basis elements of domain space, images of basis elements of domain space always spans range space of T, but set is need not be linearly independent. And every finite dimensional vector space has a basis. Every finite dimensional vector space has a basis. Very finite dimensional vector space has a basis. So if you follow with these concepts, I will just move on to the theorem, that is Rank-Nullity Theorem. You must remember the above concepts so that I will use those concepts in the middle of this proof of this theorem. Okay, what do you mean by Rank-Nullity Theorem? Suppose two vector spaces, any two vector spaces, V and W be any two vector spaces over a field, and T from V to W be a linear transformation, and suppose V is a finite dimensional. W be any vector space, but there is a restriction for the domain space. The domain space must be finite dimensional. Then rank of T plus nullity of T is equal to dimension of the domain. That is, rank of T is nothing but dimension of range space of T is nothing but rank. Dimension of null space of T is nothing but nullity, and dimension of domain is nothing but dimension of V. So V be a finite dimensional and T from V to W be a linear transformation, then rank of T plus nullity of T is equal to dimension of domain. Given, okay, let's need not necessary. V is a finite dimensional. Given V is finite dimensional vector space. V is finite dimensional. V is finite dimensional. So let dimension of, call this dimension of V is equal to, dimension of V is equal to some M, which is a finite. This dimension of V is equal to M. Clearly, N of T, N of T, null space of T is always a subspace. N of T is always a, this is nothing but null space of T is always a subspace of V. It is a subspace of V, and in fact V is a finite dimension and it has a subspace which is nothing but N of T is always subset of V. Therefore, N of T is also a finite dimensional vector space. N of T is also a finite dimensional vector space. Call let this is a finite dimensional vector space and it has a basis elements. A very finite dimensional vector space as a basis element. So let beta 1, call this beta 1 set is equal to something like alpha 1, alpha 2, so on up to alpha n are the basis elements. Are the basis elements. Are the basis elements of n of t. These are the basis element. Dimension of n of t is nothing but null space of t. Sorry, nullity of t. B1 is equal to alpha 1 are the basis elements of n of t, which implies dimension of n of t. Dimension of n of t is nothing but nullity of t. Nullity of t. This containing n elements. Therefore, dimension is nothing but cardinality of this set. This is nothing but n. Nullity is equal to n. Given V is a finite dimension, therefore dimension of V is equal to, call this dimension as m. And n of t is always a subspace of V. And in fact, V is finite dimensional, n is subset of V. This n is also a finite dimensional vector. N of t is also a finite dimension. Therefore, it has a basis elements. Call this as alpha 1, alpha 2, so on up to alpha n. And n of t is always a subset of V, which implies this containing n elements is always less than or equal to this bigger set containing m elements. N is always less than or equal to m. N is always less than or equal to m. And we can extend this to a, and in fact, V is a finite dimension, it has also a basis. And this set is a subset of P. Therefore, we will extend this to a basis of this vector space. So let these are the elements in N of T. These are the elements in V also. Let alpha 1, alpha 2, alpha 3, so on up to alpha n. We can extend this to a basis of a V. Beta 1, beta 2. Okay, this is alpha, this is beta 1, beta 2. Don't confuse with this beta 1, beta 2. So let's call this as B1. Let you didn't confuse with this beta 1 as well as this beta 1. Okay, this is B1. This is B1. Let B2 B2 is equal to alpha 1, alpha 2, so on up to alpha n, beta 1, beta 2, beta 3, so on up to, call this as some beta s. Call this as some beta s. Let B2 is equal to this set is a basis because this is a finite dimensional and these are the basis elements in null space of T. We extend these basis elements to form a basis of a vector space, or we can consider directly these elements because V is a finite dimension, it has a basis. B2 is equal to these elements. Let B2 is a basis. B2 is a basis of V. And it is a basis of V, and V is of, and dimension, since dimension of V is equal to M, which implies this N plus S. If you add this N plus S, that must be is equal to M because dimension of, because number of elements in a basis element, number of elements in a basis set is nothing but dimension. Therefore, this since we have already considered the dimension of is equal to n, therefore this basis set must contain m element. Therefore, this contains n element, this contains s element. If you add these two sets or every all elements in this set, that must be is equal to m. And we have already know that n is nothing but nullity of T. And we didn't know what mean this S. N of T and is equal to M is nothing but dimension of V. So suppose if we arrive that this S is nothing but rank of T, then it's enough. It's enough to prove that rank nullity theorem, because this nullity of T, suppose this is rank of T, then the statement is nothing but rank of T plus nullity of T is equal to dimension of domain space. So call this set beta 1, beta 2, beta s set as some s. I think I don't use s anywhere, right? Okay. Okay, call this set s. These are beta 1, beta 2. We add these elements. So call these elements must be correct in the set S. So let to collect these elements in one single set. So let S is equal to beta 1, beta 2, so on up to beta S. Since these are the basis elements in domain space, their images looks like T of beta 1, T of beta 2, so on up to T of beta S. T of beta S, call this set as T, some T. Okay, T is equal to T of beta 1, T of beta 2. Clearly, these are the elements in, are the element T is equal to T of beta 1 are the elements in R of T. Now, these are the elements in domain space. Their images are the elements in range space of T. Are the elements in R of T. Are the elements in R of T. So suppose this containing S elements. Clearly this containing S element, therefore their image is also containing S element. Suppose if this set is a basis, then and in fact this basis the number of elements in this basis is S. Therefore this is become rank of T. Dimension of R of T. This R of T is always a subspace of codomain space, and dimension of R of T is equal to S. Dimension of R of T is also S. Suppose this R of T is a basis. Suppose this is a basis, then dimension of R of T is nothing but S, which is nothing but rank of T. It's enough to prove that rank of T plus nullity of T is equal to dimension of V. Therefore, now we have to check whether this set T is a basis of R of T. Whether this set is a basis of R of T or not. T is T of beta 1. We have to check. Now we have to prove that. Now we have to prove that T is basis. T is basis of R of T. If T is basis of R of T, then dimension of T is nothing but S, is nothing but rank of T is equal to S. Prove that T is, sorry, we have used T for a linear transformation. So call this is some other name. Call this as some A itself. Let A is equal to T of beta 1, T of beta 2, so on up to. Because for a linear transformation also we have used T. We have to prove that A is a basis of R of T. To prove that any set is a basis of R of T, we have to prove two conditions. First, that set is A spans R of T. Here A is nothing but T of beta 1, T of beta 2, so on up to T of beta S. T of beta S. A spans R of T. A spans R of T. Now, basis elements of domain space are alpha 1, alpha 2, alpha 3, so on up to alpha n, beta 1, beta 2, beta S. Call in this some set B2. Okay. B2 is a B2 is equal to alpha 1, alpha 2, so on up to alpha n, beta 1, beta 2, so on up to beta S are basis elements of domain, or basis elements of domain space. And I have already told in previously that images of basis elements of domain space, images of basis elements of domain space always spans range space of T. Always spans range space of T. Hence T of beta 1, T of alpha 1, T of alpha 2, so on up to T of alpha n, and T of beta 1, T of beta 2. These are the images of basis elements of domain space. T of beta S. Images of these basis elements spans R of T. Spans R of T. But alpha 1, alpha 2, so on up to alpha n, alpha 1, alpha 2, so on up to alpha n belongs to n of T. Which implies if any element is in the null space of T, that must be mapped to 0. T of alpha 1 is equal to 0, T of alpha 2 is equal to 0, so on up to T of alpha n is equal to 0. Where these elements have become 0, we left out with, which implies T of beta 1, T of beta 2, so on up to T of beta s spans R of t, and denote this set as, and we have already denoted this set as nothing but A, which implies which implies A spans R of t. A is nothing but T of beta 1 so on up to T of beta s, which implies A spans R of t. A spans R of t. Now we have to check whether this set A is linearly independent. So this set is linearly independent. So A is nothing but this set. If you check for linearly independence, these are the elements in R of t. To check for a linearly independent, first we have to consider their linear combination. So in second case, we have to prove that A is linearly independent. A containing these elements. To prove that this set is linearly independent, first consider their linear combination. Let C1 into T of beta 1 plus C2 into T of beta 2 so on plus C something like okay, this is yes, so denote this is nothing but yes itself. Cs into T of beta s is equal to 0. To prove this set is linearly independent, we have to consider the linear combination of those elements. Clearly, this C1, C2, so on up to Cs belongs to the field elements. And in fact, T is linear transformation. T is linear transformation, which implies T of C into V is equal to C into T of V. Therefore, C into T of V can be written as T of C into V. This implies T into C of beta 1 plus, sorry, this is C1 into T of beta 1 plus T of C2 into beta 2 plus so on plus T of Cs into beta s is equal to 0, because T is a linear transformation. This condition must satisfy. T of C into V can be written as C into T of V. In fact, C into T of V can be written as T of CV. C into T of V can be written as T of C into V1. And in fact, T is a linear transformation. T of V1 plus V2 is equal to T of V1 plus T of V2. And this is again a vector, this is again a vector, this is again a vector. T of V1 plus T of V2 plus so on up to T of Vn can be written as T of V1 plus V2 plus so on up to T of Vn. This is nothing but T of C1 into beta 1 plus C2 into beta 2 plus so on plus Cs into beta s is equal to 0. Because of linear transformation, we can write this type. Because since T is a linear transformation, T of V1 plus V2 can be written as T of V1 plus T of V2. Here T of V1 plus T of V2 plus so on to T of V. This can be extended to n elements or s elements. Sorry. T of V1 plus V2 plus 1 up to Vs can be written as T of V1 plus V2. is equal to 0. If T of, this is a vector, this is again a vector, T of V is equal to 0, which implies V must be an element in null space, because if any element in null space, that must be mapped to 0. If their transformation that mapped to 0, then this elements must be belongs to n of t. Therefore, which implies C1 into beta 1 plus C2 into beta 2 plus so on plus Cs into beta s is equal to 0. Sorry, belongs to n of t. Belongs to n of t. This is again a single element. V1 plus V2 can be nothing but V. This belongs to n of t. And in fact, n of t is a null space of t, and it has a basis elements. It has a basis elements. N of t's basis elements has basis elements of n of t looks like I think alpha 1, alpha 2. Basis elements of n of t. Okay, b1 is equal to alpha 1, alpha 2, so on. All the basis elements of n of t. Okay, alpha 1, alpha 2, so on up to alpha n, alpha 1, alpha 2, so on up to alpha n are basis elements in n of t. Since these are the basis element and this is a one vector in n of t, basis mean any element of this vector space can be written as linear combination of those basis elements. Suppose if any set is basis for this n of t, then any vector in n of t can be written as linear combination of those basis elements. Therefore, this is again a vector in n of t, this is again a element in n of t, and this element C1 into beta 1 plus C2 into beta 2 plus so on plus C and Cs into beta s. This element, this is the element in n of t, and this element also can be written as linear combination of basis elements of this set. Basis elements of this set are alpha 1, alpha 2, so on up to alpha s, alpha n. Their linear combination, call this some set as some d1, some d1 into alpha 1 plus d2 into alpha 2, so on plus dn into alpha n. This is a linear combination of this basis element, and this vector, this is again a vector, can be written as linear combination of these basis elements. Therefore, shift this to RHS, we left out with d1 into alpha 1 plus d2 into alpha 2 plus so on plus dn into alpha n minus c1 into beta 1 minus c2 into beta 2, c2 into beta 2 minus c3 into beta 3 minus so on minus cs into beta s. This is a linear combination. This is a linear combination. Linear combination of vectors alpha 1, alpha 2, so on up to alpha n, and beta 1, beta 2, beta 3, so on up to beta s. And these vectors are, and these are field elements d1, d2, d3, c1, c2, so on up to c3, so on up to cs. These elements are in the field. These elements are in the field. These elements belongs to field. These elements belongs to field, and these are and these are basis elements of basis elements of vector space V. basis elements of vector space. We have to checking this set as a linearly independent. Okay, these are basis elements in vector space. Since these are basis elements in a vector space, if their linear combination is equal to 0, basis means that set is linearly independent. This set must be linear. This set is a basis elements of V, basis elements of vector space. Therefore, if we have to, this is nothing but a linear combination of those basis elements. If we consider linear combination of those basis elements, then their field elements must be is equal to 0 because of this basis set. Because this is a basis set of V. If you consider those linear combination of those elements, and the scalars must be is equal to 0, which implies d1 is equal to d2 is equal to so on up to dn is equal to, this is number c1 is equal to c2 is equal to so on up to is equal to cs is equal to 0. We have considered linear combination of, which implies we just want that c1 is equal to c2 is equal to so on up to cs is equal to 0. We have checking the linear, considering the linear combination of this set. To check for linearly independent in the set A, we have considered their linear combination. This is linear combination. These are the scalars. Element belongs to field. We are considering the linear combination, and in this linear combination, every scalar is 0, which implies this set is linearly independent. Which implies A is linearly independent. A is linearly independent, and spans R of t. This is linearly independent in R of t itself, because these are the elements in R of t. A is linearly independent, A spans R of t, which implies A is basis. A is basis of R of t. A is basis of R of t. And if A is basis of R of t, dimension of A is equal to is nothing but dimension of R of t. Dimension of R of t, this containing S elements. In the set A, it has S element. Therefore, dimension of this, cardinality of this set is nothing but S. So, we have proved that S is nothing but dimension of R of t, and this is nothing but rank. Dimension of R of t is nothing but rank. So from this, I think call this as some equation 1 or 2. Okay. N plus S is equal to N. N plus S is equal to M. This N is nothing but nullity. S is nothing but rank. So call this as some equation 1. So equation 1 implies equation 1 implies rank of t plus nullity of t. S is nothing but nullity. R plus S, sorry, okay, not on this. Rank of t plus nullity of t is equal to dimension of domain, that is dimension of V. Rank of t is denoted by R of t plus nullity of denoted by some N of t. is equal to dimension of V. Rank of T plus nullity of T is equal to dimension of domain space, and that is nothing but V. So just I want to glance this one. So V and WB vector spaces over a field F, T from V to WB linear transformation, and suppose that V is a finite dimension, then we have to prove that rank of T plus nullity of T is equal to dimension of domain. So dimension of R of T plus dimension of N of T is nothing but dimension of V. V is a finite dimensional vector space, therefore I call it as it containing M elements, and N of T is a subspace of T, and it is also a vector space. Call this set containing N elements. Therefore, I extend the null basis of null space to a basis of a vector space V. Therefore, this is nothing but I call this as a basis elements of domain space. So, I have taken this set A is equal to T of beta 1 so on up to T of beta S. Suppose this set is a basis elements of R of T, then this dimension of those basis elements is nothing but rank of T. Therefore, I have to check whether this set is a basis or not. So, to prove that this set is a basis, first we have to prove that the set spans R of T. Vector space, here vector space is nothing but R of T. Therefore, A spans R of T. We have proved that A spans R of T, and A is linearly independent. We have proved that one also. Therefore, dimension of those R of T is nothing but rank of T. Therefore, rank of T plus nullity of T is equal to dimension of V. So if you have any doubts, you can comment on the comment box. Okay, thank you.